My paper is Improving Togetherness Using Structural Entropy. A major theme in the study of social dynamic is the information of community structure on social network. For example, the network contains several distantly connected regions that are sparsely linked between each other. In this paper, we investigate the network integration process in which edges are added to dissolve the communities into a single undefined network. In particular, we studied the following problem, which we refer to as togetherness improvement. Given two communities in the network, alternately establish new edges between the communities so that they appear as a single community in the network. Towards an effective strategy for this process, we employed tools from structural information theory. The aim here is to capture the inherent amount of structural information that is encoded in the community, thereby identifying the edges to establish which will maximize the information of the combined community. Based on this principle, we designed an efficient algorithm that alternatively establish edges. Experimental result validates the effectiveness of our algorithm for network integration compared to the existing benchmark. Introduction. A social network consists of a set of individuals and their social bonds, forming a graph that inhabits a range of non-trivial statistical properties. Community structure amounts to one of the most prevalent properties of a social network. This property asserts that the graph can be broadly viewed as consisting of several distantly connected subgraphs called communities that loosely connected between each other. Understanding the community structure provides key insight on social composition of the society. As social bonds can be seen as channels of interactions and pages of information and knowledge, communities are decisive in determining important social and behavioral traits such as social cohesion, self-identity, and emergency for norms and trust. A proposal themed in study on social networks is dynamic of social ties. Countless schedules exist where needs arise for updating the social bonds between individuals, thereby changing the graph structure. Many of these schedules would involve intentions to integrate two communities into one. By take for example, business mergers and acquisitions, which see two companies dissolved into a single entity. The marriage between two large families which complex relations, the emulation process which when immigrant arrives at a new country, and the healing process between two divided political fractions of a government, creating a smooth affiliation between two disjoint communities in this schedule is a common desirable outcome. which enhance the building of the common grounds, manual understanding, cooperation, and conflict resolution. The concepts of togetherness aim to capture the level of unity between two communities. This concept is defined in the context of network integration. In a nutshell, network integration corresponds to process where communication channels are built, creating opportunities for interaction between individuals who otherwise belong to different communities. Our contribution is motivated by the discussion about we investigate network integration and togetherness in the graph as a salient community structure. Our contribution includes first, we invoke the pan-structural information theory and borrows from their work the notion of structural entropy to qualify the amount of uncertainty with uncertainty with a graph. This notion allows us to determine how much information is gained through the community structure, which lead to our togetherness improvement problem. We discovered an interesting phenomenon, namely maximum degrade principle, that links information begins through the community structure with the degree of nodes in the community. Through this finding, we propose an efficient algorithm TIE for solving the togetherness improvement problems. Finally, we demonstrate the effectiveness of our algorithm using experiments on both real-world and statistic network datasets. Network immigration is a process that introduces a sequence of new edges to the graph to improve togetherness. More formally, it makes two community I and community G. The process intensively add edges that connect members of I and the member of G. Our goal is to add as few edges as possible before they can be regarded as a single community. This figure encapsulates an example of a network integration using Zertre curated club, a standard benchmark dataset of community detection. We use Luan method to identify the community of this structure. It can be seen on the left. There are 4 communities with different colors. After we adding 9 new edges, and the blue community and the purple community are merged into one. It's shown on the right. And the information gain of the community structure P is shown on this page, and our goal is to maximize the information gain of the structure P. This is the principle we proposed, the mass degree principle, and it links the information gain and the edges of the nodes together. So we can find the the nodes with max age and link them together so that we can use less time of our algorithm. And this is our algorithm. And this is our examination experiment. First is dataset. answer the questions by performing network integration on real-world and synthetic datasets. Table 1 provides a key statistic of the real-world dataset. Film Trust is the user trust network of the Film Trust project. Email is an email connection network that at a university. Quora is a citation network of the scientific politicians, and Facebook is a mainly liked network among Facebook pages. And we also establish the LFR modes to generate the number of synthetic networks, which is shown in Table 2. And the permutator key for the LFR mode refer to the desired average degree, and the mu is the function in inner community ages. And the benchmark algorithm includes the random add ages algorithm and add ages by using the min degrade nodes, adding ages using the max betweenness degrade nodes, and the center pair algorithm. And the performance index we use the index like this. This graph and this table shows the results of our experiment. Figure 2 compares performance to togetherness improvement as more ages are added. The more ages, as more ages are added, both the Smax and the FE score increased for our TIE program algorithm. TIE clearly outperforms the benchmarks, both on the Film Trust, email, and Quora, and comparable with the best strategy on Facebook. On Facebook, several algorithms all quickly achieve the good performance, and therefore the advantage of the TIE is not clearly shown. Our statistic LFR network with 100, 500, 1,000, and 10,000 nodes, we added a certain ratio of ages between the communities. Table 3 lists the resulting Smax scores. TIE clearly outperforms benchmarks in all cases, and max betweenness was not shown to deal with the high computations cost and lack of space. Efficiency, we run this time various time for the age added, which value is time of repeating 50 repeated experiment. Random adding ages using the shortest time. TIE algorithm runs in a reasonable time for all cases. And conclusion and future work. This paper studies the togetherness improvement problem at the aim of integrate communities in the social network by exploring tools from structural information theory. The reintegration of the communities can be reflected by structural entropy, where information gains provide the keys to improving togetherness. We designed a efficient TIE algorithm for the task, which is validate on both real-world and statistic data sets. Future works include extending the problem and method to detect attribute or weighted networks, as well as considering other strategies. for example, rewriting for the network integration. Thanks for watching.